Welcome back. In this session, we are going to talk about the bivariate and multivariate analysis. So far we are looking at only single variable, right? Now let's shift our focus from single variable and see how variables interact with each other. This is where bivariate and multivariate analysis comes in. So we have bivariate analysis. This is a study of a relationship between two variables at a time, like watching two dance partners move in a scene. So we use detect any correlation between patterns. For example, whether increase in net income, whether it has impact on total assets, and also identify the potential dependencies between the features, where one feature might influence the behavior of another, right? In the multivariate analysis, this is where things get richer and more complex. So where we are exploring the interaction among three or more variables. It's like, listening to your entire orchestra rather than just a song or maybe some in a small duet. So here we can uncover the multi-variable relationship between that wouldn't be obvious in pairwise analysis. Basically, this reveals the hidden patterns of groupings and understand how multiple features collectively impact an outcome like bankruptcy in your case, in the exam data set we are taking. And why do this matters? Because these analyses act like a relationship between counselors for your data. They help you to decide which features are truly relevant and which are just noise. So why this is more useful? This will helps you when you're building the model. It helps you prevent the overfitting by removing unnecessary variables, and ultimately they boost your model's predictive power and reliability. So before you build a model, no, you should do your relationship checks. Bivariate and multivariate analysis are essential steps in exploratory data analysis. So as we dive deeper into bivariate and multivariate analysis, it is important to understand that not all variables pairings are the same. The type of data you are comparing, whether it's a numeric or categorical, determines which techniques you should use. So let's walk through some of the combinations. So first we have numeric versus numeric. This is the most common use case where both variable represents a continuous value like income, age, asset or profit, right? To explore their relationship, we use tools like either Pearson or Spearman correlation, scatter plots for visualization trends like that. And next we have categorical versus categorical. Think of this like comparing groups like gender versus loan approval or industry versus bankruptcy. So the tools we use for a categorical versus categorical tools where you comparison is cross tabulation type of tools, or we can use something like chi-square test to check the statistical association, and heat maps to visually reveal the relationship between this data. Then we have a categorical versus numeric, like comparing average income across industries or distribution of profit by credit ratings. So here we are interested in how a numeric variable behaves across categories. So again, we use the box plots we discussed in the previous slides, and also like group level summaries like mean or median per group. So selecting the right pairing techniques eliminates the hidden patterns that might otherwise go unnoticed, and it sets the stage for deeper insights as we move on to the multivariate analysis. Next, we'll explore the numeric variable pairs, like what are some techniques to identify the relationship between two numeric variables or features. Now let's talk about one of the most widely used tool in bivariate analysis, Pearson correlation. Pearson correlation coefficient, often denoted as R, is a statistical measure that helps us to quantify the strength and direction of a linear relationship between two numeric variables. Imagine you want to know if the companies with the higher retained earnings are also more profitable, or if companies with the most debt tend to show lower returns. Pearson correlation gives you a single number between -1 and +1 to answer these kinds of questions. A value close to +1 means a strong positive linear relationship between, as one variable increases, so does the other. A value of 9 -1 means a strong negative relationship, as one goes up, the other goes down. A value of 0 suggests that there is no clear linear pattern between them. So But we need to keep in mind that we are making two important assumptions here. The relationship between the variables should be linear, a straight line pattern, and the variables themselves should ideally be normally distributed. If either of these assumptions doesn't hold, say your data is skewed or has curved trend, Pearson might underestimate or misrepresent the true relationship between. In those cases, we have another statistical measure called Spearman correlation, which we'll talk in the next. So for now, just remember one thing. Pearson R is the go-to tool when you're looking for a linear dependency between two continuous variables. Now let's look at how Pearson correlation behaves. Let's understand more details about that. So first, before we talk about Pearson correlation, let's understand what is covariance. Covariance measures how two variables change together, whether they rise and fall in sync or move in opposite direction. At the top, you will see the formula for Pearson R. It calculates the covariance between two variables normalized by their standard deviation. In simple terms, it tells us whether how strongly two variables move together in a straight line relationship. Now let's break down this into visually. On the left, we have negative correlation. As one variable increases, so other will decrease. Imagine something like debt ratio versus retained earnings. More debt might signal less retained profit. So in Pearson term, this value would give us R as close to -1. In the middle, we have a no correlation. The dots are scattered randomly. There is no clear trend or pattern between these two variables, and R would be close to 0. On the right, we see a positive correlation. As one variable increases, so does the other. So think of net income and return on assets. A strong linear relationship like this would give us the R value close to +1. So in summary, -1 means perfect negative correlation, 0 means no linear relationship, +1 means perfect positive relationship. So what is the key point? As I told in this previous slide, to summarize, Pearson correlation is best used when you believe the relationship between variables is a linear. If your data has curves or ranks instead of direct linear relationship, that's when we have to use a Spearman, might be better choice, and we'll talk about that next. So before we talk about the Spearman, okay, let's talk about the monotonic relationship. A key concept that helps better understand why, when and why we should use Spearman correlation over Pearson. Right? A monotonic relationship is one where the direction of relationship between two variables is consistent. It is either always increases or always decreases, but it doesn't have to follow the straight line. So it's not about the linearity. That's very important. It's about the order of the values being preserved. So even if the rate of change isn't constant, as long as higher values of one variable consistently relate to higher values or maybe lower values of another variable, it is a monotonic relationships. So here are like some few examples. For example, as steady time increases, the test score tend to increase. The increase might not be perfect linear, but the trend is upwards. Another example is as a company debt ratio increases, the likelihood of bankruptcy also tend to increase. Again, a clear upward direction. On the flip side, we have monotonic decreasing. As a credit rating drops, the risk of default increases. So even though the variable move in opposite direction, the relationship is still consistent, just in reverse order. So now that we understand the monotonic relationship, and let's dive into the next correlation measure, which is a Spearman correlation, which is designed specifically to capture these type of pattern. So Spearman correlation coefficient, often denoted as a P or RS, measure the strength and direction, that is very important, of a monotonic relationship between two variables. But here is a twist. It uses ranks, not the raw data values. So how does it work? First, Spearman ranks all the values for each variable from smallest to largest. Then it calculates the Pearson correlation, but on those ranks instead of the original values. Then this lets it detect whether one variable consistently increases or decreases as other does. Even if the relationship is curved and not linear at all, so this will help you detect that relationship between these two variables. But when should you use Spearman over Pearson? So if your data isn't linear, Spearman can still pick up meaningful patterns. If you're working with ordinal variables like credit scores or education levels or survey responses, Spearman is ideal. And if you have outliers, Spearman is more robust because it ranks are less sensitive to extreme values than actual numbers. So overall, if Pearson is a go-to for the linear relationship, Spearman is your the go-to for the when the direction matters more than the shape. You want to understand whether when I increase the value of some variable, whether decrease the value of others, or whether when increases this, whether other also increases. So what is important in Spearman is a direction. So now let's get back to our Jupyter notebook and then do bivariate analysis on our data. So let's first load all the libraries, pandas, numpy, load the data, standard thing we do. Let's check the info and then we will do the check the missing values. We don't have any missing values, we are good. Before that, let's see how many categorical values are there, how many numerical columns in our data set. So we are having pretty much every data, every feature we are having here, all of the numerical columns, because it's a financial data, all financial ratios and financial numbers. So obviously, and then next we'll go ahead and compute the Pearson correlation. Before that, we will visualize the Pearson correlation matrix in a heat map. Okay, so this will tells you how these variables are correlated as per as per the Pearson. You can see that the way to read the data is in the middle line is shows strength between two variables. Now depending upon the color what you see in these cells, that will tell you whether which is highly correlated or not correlated. For example, it is a -1 to +1, you are having the data. If it is highly correlated, you'll see that it is a dark blue here, or it could be this dark gray, brown color, depending upon the correlation. Now let's see, as per the Pearson, what are the highly correlated features. That means where the Pearson correlation metrics are, which is greater than 0.8. So these are all the variables which are, this is a variable 1 and this is a variable 2. Of course, this is not properly plotted here. This is a variable 1, ROI interest and depreciation before, and then this one. So these two are all highly correlated variables. For example, you can see that the fourth one are return of assets before interest and percent after tax and net income of total assets is highly correlated, right? Now we have seen this is the as per the Pearson what is the highly correlated. Now let's also see how does the Spearman correlation matrix also look. So let's visualize first Spearman correlation matrix. You can see that the Spearman, there is a difference between your heat map between the Spearman and Pearson, right? Because Spearman is good. Pearson, as we discussed, it is works only when the relationship between the variables is linear, right? But when you're having 96 features, not everything is a linear relationship. There could be some variables might not have linear relationship. That's why you are seeing entirely different heat map in case of a Spearman instead of a Pearson. Now let's see, as per the Spearman, what are all the highly correlated matrices. In the end, we are going to plot the graphs next to each other and see like how the features different between the Spearman and Pearson is going to be. And next we are going to compare the Spearman and Pearson, like what is the correlation comparison of a Pearson and Spearman high correlation, which variables are variable and variable 2, what is the correlation Pearson, what is the correlation Spearman. You can see that some variables it says nothing, okay, but Spearman shows negative relationship of -0.95. So there is a lot of difference between the correlation, lot of variables where Pearson is not able to detect that correlation, Spearman correlation could detect that, right? Now for our analysis, let's create some categorical variables. If you see our data set, we don't have any categorical variables. So of course we'll create the categorical variables now, and we are going to use them in the coming slides when next we are going to talk about the cross tabulation everything. So we'll use at that time, but for now let's create the some categorical variables for our cross tabulation purpose, so that we can see how the I'm going to talk about cross tabulation in the next slides, but we'll discuss more when we will come back to this when we discuss about the cross tabulation. So for now, this is a summary. We discussed about the Pearson and the Spearman. Now we can see that both are different. Spearman works when the relationship is not a non-linear also, but Pearson, the relationship has to be linear. So next we are going to talk about the categorical and categorical variable pairs. So what are categorical and categorical variable pairs? Okay, and this is one of the key part in the bivariate analysis. So when both variables are categorical, we are not interested in calculating the correlation coefficient like we do for numerical data. Instead, we want to study how categories related associate with each other. For example, think something like this, right? So do people with the different credit ratings tend to go bankrupt at different rates? Or is there a pattern between industry sector and default status? So the key insight here is that these relationships are not measured using correlation, but rather using the frequency or proportion comparisons. So we often use cross tabulation tables or contingency tables to explore these relationships. So let's look at a simple example given below. So we have broken down the customer by credit rating, whether they are bankrupt or not bankrupt. Among the customers with low credit rating, 30 are bankrupt and 20 are not. With a medium rating, 10 are bankrupt and 40 are not. Among high credit rating individuals, only 2 are bankrupt while 98 are not. So this cross tab instantly reveals a pattern. So low credit rating is associated with a higher bankruptcy rate. So remember, when you are working with the two categorical variables, we need to ask ourselves, is there a pattern in how these categories interact? And using this cross tabulation will actually reveals that story very clearly. So when we are working with the categorical variable pairs, the goal is to explore whether there is a relationship between different category combinations. So we have several effective techniques at our disposal. One is that cross tabulation. This is the simplest yet most powerful tool we have seen in the previous slide. Think of it like a frequency grid. It shows how often each combination of category values occur. It helps you quickly spot patterns or imbalances across groups. So visual techniques. Tools like stacked bar chart or mosaic plots are great for visual learners. They turn those cross-tab frequencies into proportions, helping us to see which categories dominate or lag behind in visual format. Another statistical test which we use is chi-square test, which is this will check what is the statistical significance. It tells whether the difference we see in category frequencies are likely due to chance or is there a real relationship between these two variables. Next one is Cramer's V. If chi-square tells us whether an association exists, Cramer's V tells us how strong that association is. From 0, no association, to 1, which is a perfect association. It is especially useful when your contingency table has more than 2 by 2 combinations. So depending upon whether you want to summarize, visualize, test or quantify, we have to choose the right tool for categorical pair analysis. Now let's talk about one of the most simple intuitive tool, which is cross tabulation, right? Which is very easy also to understand. So what is cross tabulation? It is a technique used when both variables are categorical. It helps us to check if the groups are related by displaying their frequencies in a contingency table like the one you see here. For example, in the table, we are comparing credit rating with bankruptcy, right? We saw same table. So you can immediately spot that people with a low credit rating are much more likely to be bankrupt than those with a high credit rating. So now let's break down the benefits of this cross tabulation. It visualizes group patterns clearly, which categories co-occur and how often they occur. It helps us to identify risk areas like which segments are more prone to default or churn. And most importantly, it supports data-driven decisions, allowing us to tailor strategies based on the category behavior. So crosstabs are incredibly simple but powerful. They are often the first place we look to explore association pattern before diving into statistical tests like chi-square test. So next, let's talk about stacked bar chart, which is very intuitive, I think very easy to understand. You might have seen this multiple times in a lot of places. So what exactly is stacked bar chart? A stacked bar chart displays a total count of a primary category, but breaks down into subgroups. So you can see both the overall number and distribution within each group. For example, if you are analyzing the liability asset flag against the bankrupt status, so we are having something like low, medium, high. So each bar represents one flag value, 0 or 1 or low, medium, high. And within the bar, we stack the count of bankrupt versus non-bankrupt. So why this is helpful? Because it shows both absolute frequencies and relative proportions. So you can quickly spot the imbalances. For instance, a tall bar with a large red section, which is a bankrupt, signals us that higher risk under that flag. So how do you read this flag? Look at the height of each full bar to compare total records per group. Then examine the segment inside the bar to assess how outcome like bankruptcy varies within each group. So it's just not about how many, it's about how the composition changes. These charts are simple but powerful for identifying category based association or risks or behavioral patterns. Now let's examine a simple example to understand the staggered bar chart. So you assume that you have two classes, class A and class B. And after the math test, you categorize the students into pass or fail. Now you want to visualize how each class performed. We draw a stacked bar chart. You draw one bar for class A with the bottom portion 20 pass, top portion 10, which is failed. You draw one bar for the class B with bottom 15 and top 15, like pass and fail. What we can see instantly, class A has more blue passed than the red failed, doing better overall. Class B has equal parts pass and failed, which needs attention, right? So you can visually, by looking at the chart, you can immediately see that this particular class has got more pass than fail. In one class they are equally distributed. So you can visually compare both the total students and success rate per class in one view, and it helps you to see both absolute numbers and proportion. It's just not that you are seeing the proportion as well as the absolute numbers on the graph. So total student per class, which is the bar height. How outcomes are split, which is the bar segment. So you can see both the number and the proportionality in one visualization. Now let's talk about one of the most important statistical tool we use in EDA for categorical variable analysis, which is a chi-square test. So the chi-square test is a statistical method used to check whether two categorical variables are associated. In simple terms, it tells us if there is a meaningful relationship between these two categories. For example, if there is a link between the credit rating and bankruptcy. To do this, it compares the actual count we observe in the data with what we would expect to see if there were no relationship at all. So here how it works under the hood. It starts with something called contingency table, also known as a cross tabulation, as we have seen in the previous slide. This is just simple grid showing how two categorical variables intersect. For instance, how many low credit customers went bankrupt versus who didn't. The chi-square test calculates expected values assuming there is no relationship between the variables, which is very important to know. Okay. Then it compares those expected values with the observed values using this formula, which is summation of observed minus expected whole square divided by expected. This gives us a chi-square statistic, but that doesn't tell you whole story. Now comes the part where everyone cares about the p-value. The p-value tells us how likely is that the observed difference in the contingency table happened just by chance. A small p-value, typically less than 0.5, means that the difference is statistically significant. That's our green light to say yes, there is a likely real association between these two variables. But the p-value is very large. We don't have enough evidence. The difference might be just random or noise. So how this is useful in real world EDA? Take the what we are doing like credit risk modeling as an example. If we use chi-square test to compare default rates across the credit tiers and get a significant p-value, we just uncovered an important relationship worth modeling. The chi-square test is foundational when dealing with categorical features. It helps us to know which variable has got more predictive power and which don't, especially before we get into the modeling. Now let's get back to our Jupyter notebook. First, draw some crash tabulation for couple of variables so that you can better understand. You can see that because bankruptcy or target variable, we are trying to compare the bankruptcy with our ROI category, and then we can also see that how the bankruptcy ROI at low, medium, and high, how they are actually related to the bankruptcy. 0 means not bankruptcy, 1 means bankruptcy S, right? And then we are actually comparing with debt ratio category, right? So you can see that the banks with low debt ratio also has got low chance of going bankrupt, right? You can instantly see from this one. And let's draw for another one, and before we draw that, we can also draw a stacked bar chart here. Now we can see that the stacked bar chart, which is now the whole bar is split across bankrupts and non-bankrupt. Now this is ROA category, return of asset category, and then we are having low, medium, and high values. We are seeing what is the percentage of bankruptcy versus non-bankruptcy. Next, we will see the bankruptcy with the debit ratio category, like this. Now you can see that we are basically, what is, as we discussed, you can see that visualization, there is there are no companies in the medium category which didn't go bankrupt, but if you can see that debt ratio is high, they are not bankrupt. But if they're having low, there was not bankrupt. Very few companies went bankrupt here, but in the medium category, pretty much every company went bankrupt, right? So like that we can see. And also in the we could draw this for multiple things, and we'll also do chi-square test, so which tells, now you can see that p-value which is significant because now is all 0.05. This is very significant relationship between these two variables, which is bankruptcy and ROA category. And then we'll also do chi-square test for some more variables here to understand whether they're significant or not. You can see the chi-square is 60.0.43 and p-value is this, and then degrees of freedom. So let's, I think maybe I didn't talk about degrees of freedom previously. So what is degrees of freedom? So let's talk about that. So at high level, degrees of freedom represents the number of independent values in a data set that are free to vary when calculating a statistics. So simple analogy. So imagine you and say your 3 friends are splitting the restaurant bill. The total is say fixed at $100. Now you can each decide how much to pay up to a point. The first 3 people can pay whatever they want, but once 3 amounts are decided, the 4th one is fixed. So now it has no freedom to vary. Why? Because the total amount is 1000. So in this case, even there are 4 people, only 3 people amount what they contribute are free to vary. The 4th person, what he is supposed to pay is fixed. That is called the degrees of freedom, right? And before we do that, let's also compare. We have done the Pearson and Spear correlation matrix, and we'll compare in side by side between the Spearman and Pearson correlation, how they are. I think, yeah, of course we have done this already. So total variables most correct the bankruptcy in case of Pearson, and you can see Spearman. Of course there are some differences. For example persistent EPS in the the last one, this is there. Pretty much all of them are same here. Some of them are varying. Some of them which Pearson couldn't catch, Spearman could actually say. For example, debt ratio as per Pearson is there, but as per Spearman, for example, this one, continuous interest rate is not there in the pre-after tax. There's a 0.22, but as per the Pearson, that relationship, it doesn't exist, right? So there is a slight difference between the Pearson and Spearman, depending upon how the linearity or non-linearity within your data. So coming up, we are talking about outlier detection, which is very important. We should detect how are the outliers in our data, what are the outliers in our data, that so that we can either eliminate them or we can see whether those need to keep them, or are they adding to, are they going to, the model can overfit or underfit based on outliers also. So we are going to talk more about that next sessions. Thanks for watching. See you again next session.